Good morning.
Morning.
Morning, doctor.
Sorry, guys, if I'm a bit late today. By the way, before I forget, I believe last week I got a notification from Microsoft Teams that someone from this class was trying to reach out. Sorry, I have troubles with that, I believe, because I have a personal and work account. So even that notification vanished. So please use email to contact me. Let's wait for one more minute. Okay. So today we will discuss some advanced signal processing steps inside the GPS receiver. Normally you will not deal with unless if you will work on pure GNSS signal processing or the ultra tightly coupled version where you will use like in this case we collect the actual samples like the numbers at very low level of measurements or domain. We collect the samples and we work on them to generate the high level measurements that are the range and the Doppler, uh, sometimes also the what we call accumulated range. And so using those like steps, we can retrieve the received GPS signal and extract key information for computing position, velocity, and time information. Here, just a reminder again, you have seen this, I believe, more than one time. The GPS constellation consists of many satellites, typically 24 in medium Earth orbit. That means tens of thousands of kilometers higher than Earth's surface. And these satellites continuously or consistently transmit signals in one-way fashion, like from the space to the Earth surface. That's why that's one of the challenges here. There is no two-way communication so that we can acknowledge the receiver or we can, for example, tell the transmitter there was error detected or so. So it's the sole task. The main task is the sole responsibility of the receiver itself to extract the given information on that signal. And since all satellites use the same frequency as we discussed before, distinguishing these satellites becomes like another challenge. The GPS receiver or the system operates in the L-band frequency using the code division multiple access or CDMA modulation technique. In this technique, each satellite is assigned a unique code to distinguish or identify that satellite by the receivers, since they share the frequency band. And because GPS signals travel like large distances, they arrive at the receiver antenna extremely weak. They are like exhausted. And for the matter of comparison, a light bulb with 100 watts is 10 to power 18 times stronger than a GPS signal near to the Earth's surface. This makes the GPS signals or GNSS signals indeed like highly vulnerable to interference and jamming sources, either like unintentional or intentional ones. We have seen this figure together before. This is the structure of a GPS signal. The navigation message, which comes at 50 hertz, as you see here. This is for scaling issue. We show like as if we are showing 20 milliseconds of in time. That covers 1 bit at a rate of 50 hertz. So that's the frequency of the navigation message. So it comes at a very low sampling rate. The code bits, which comes at 1 megahertz, are combined together with the uh, original navigation message bits using XOR operation. And the result, the output, is modulated or imposed on top of the carrier signal using phase shift keying, PSK modulation technique. In this technique, if the resultant bit from combining the navigation message bit and the code bit is 0, so the carrier or the phase of the signal is left intact. No change will happen. But if the resultant bit is 1, then the signal phase is shifted by 180 degrees. As this is not like very accurately reflecting, but I believe you understand. Like if the signal phase was moving up like this, it will move down instead. That means we shift the signal in phase by 180 degrees, or pi if you wish. With those combinations, this is how the GPS signal looks like. This is the structure of the signal now. This term here for the amplitude or the signal power, this represents the bit from the code. This is the code bit at time t, XORed with the navigation message bit at time t, which is d of t, all for the same satellite K in this case. And this is our frequency, the L1 frequency, for example. This is cosine omega t. That's the carrier. Any question about this before we go further?
How do we how do we choose the amplitude? Like root 2 p of power of carrier. What is the power of carrier? Or to have 128 dB near the receiver? Is
Uh,
it a
s-
constant number or
Sorry, I didn't get this part. This is here for the simplicity. We take this branch or portion of the signal with this is the factor for the cosine side, by the way. But there are derivations where you can see the how the power is calculated, what power C is. And just here for simplicity, we didn't break the details, but this is the scaling factor or the magnitude. So you are saying how come it's very low at the receiver side, or what was the question?
no? No, I was saying why is root of 2 PC, not PC itself. Power of
Yeah,
why it's yeah. Okay, I can see it in the verification.
all right, you got it, or
Yes, thank you.
no worries. So how this unique pattern of bits or the code on the can help us? Those are those patterns of codes are uniquely selected so that when the satellites like share the same frequency, they still like the receiver can still distinguish between two satellites. How is that? Those like codes are kind of orthogonal, almost orthogonal, which means the cross correlation between two different codes is close to zero, which is minimizing the interference between them. If you look at this model here, if we take a code, the code, by the way, is 124 bits, right? Those bits are combinations of zeros and ones. If we take the code of satellite K, and we slide through another code, for example, a satellite L with a shift of n. This n could be any number, so that the sum of these two, because they are totally different, the sum should be minimum. It's not a zero, of course, but it should be very trivial or small value. That's called the cross correlation. So there is no interference. If we have many satellite signals present in those samples we have from the antenna output, they shouldn't interfere with each other. They shouldn't even affect each other. That's one property here. This is very important. This is to distinguish between the two satellites. Now, the other thing, how we can raise the signal power at the receiver, because the signal is very weak and it becomes like below the noise floor. How can we bring it up? We generate a local replica of the same expected signal, or the code, I mean, and we exploit this other important feature, which is the autocorrelation. The autocorrelation, like when two codes the code itself correlates strongly with itself only when perfectly aligned in time. So if we take one code for satellite K and another version of that, like if you look at this might help here. They only give a peak when they are totally aligned. And when they are shifted by even 1 bit, this n could be 1 bit, for example, integer or 2 or 3 or 4. If they are shifted, we will always get very small amount. That means if they are shifted in time, they will be totally different. But once they are on top of each other, we'll get a peak. And that means in our real applications, if we found a match, if we found a peak like this, that means, oh, we could detect that satellite signal in those samples we collected from the antenna. Are those clear enough? Those are the very important characteristics about those. They call them sometimes golden codes, by the way. That's how we can extract the signal and we detect it. GPS signals, we know that they are delayed due to propagation time, right? But they are also shifted in frequency due to Doppler. We mentioned this before. So here's like this was the transmitted signal structure here. But look at this, the received signal structure here. You will see the delay. This is supposed to be the navigation message. Bit D of t, it's delayed by the propagation time minus tau. This applies to the code as well, and the carrier will be shifted in frequency by the Doppler amount. So instead of the intermediate frequency, we'll receive the carrier at the intermediate frequency plus a Doppler shift, and we mentioned FD could be a plus or minus, means the shift is to like it lowers the signal frequency towards zero, or it moves it up or away from the zero. And this is the phase of the received signal. N is the noise term. And that's exactly why a GPS receiver is a sophisticated communication device. Because in addition to the standard communication steps we see here, we have pre-filtering, pre-amplifier, down conversion, AD, analog to digital converters. Those apply to most communication systems. However, the last two steps here, the ones we will talk about today, acquisition and tracking, are kind of like limited to GPS receiver, or this type of one-way modulation using this type of one-way communication using this type of modulation. So the acquisition step, we'll see more details shortly. So this acquisition step coarsely estimates signal delay and frequency. The tracking, on the other hand, like continuously refines those initial estimates for accurate navigation. And these two steps, as you see here, they feed the navigation processing. So these two steps allow us to determine satellite receiver range and the rate of change of the range which in turn lead to the calculations of position, velocity, and time information. Any questions about this? We mentioned before those stages to combine together, we call them front end. So you can now find some like front end units which can provide you with the digital IF signal in I and U formats, like in phase and quadrature samples. And from there, you can feed this information into even a software receiver in Python or MATLAB and process the signal and apply acquisition and tracking and then navigation stages. But these normally, by nature, they need to be done in hardware. Any questions about this? So to find the code to search if like a satellite signal is present, we need to apply the acquisition step or process. Signal acquisition involves like searching for the carrier and the code face of each satellite. So as you see here, the search space is two-dimensional. The code face represents the delay, the signal delay, which helps us in calculating the range between the satellite and the receiver. The other dimension is representing the Doppler shift, which helps us like estimating the frequency of the received signal. Why do we need those? The range or the delay will represent the range. I can measure the range. I can measure exactly the transit time when I can track this delay on the signal. I need the frequency so I can demodulate the signal correctly. If I don't know the shift in Doppler, I cannot demodulate the signal, because what I do at the receiver, when I receive that transmitted signal with that cosine wave, I multiply it with another cosine wave generated locally. If that frequency is known to a good extent to me, I can demodulate, I can remove that cosine. When I multiply the two cosines, I get the cosine, the difference. When the difference is very small, if my estimation is good, that cosine zero or the cosine small amount will be 1. So I get rid of that and I keep only the navigation message and the code. And since I know which code is this, I can also remove it. That's why I need to estimate both the code face and the frequency. So when I get a match, if I search for a satellite in the samples I get from the antenna, if I search for a satellite signal, knowing roughly the code of that and the frequency shift, I will get a peak. When I am too close to that, I get a peak. Other than that, I get very small amount. Why is this? This is due to the properties we discussed in the past slides today. So there is a unique peak. This peak could be sometimes destroyed, or you might see other peaks if you have a major error source like jamming or multipath or even ionospheric errors sometimes affect this severely. But in normal and in good like clean conditions, you will get one peak in this two-dimensional space. So how is this done? There are three types or methods to do this search, the signal acquisition. By the way, it's a very intense process. So the most common approach is what's called serial search signal acquisition algorithm. This is the most, by the way, the most common, although the slowest among the other, as we will see shortly, the other two, but it's the most common, I believe. In this case, what we do, we generate a local replica of the signal we generate, we know the code, right? We are now guessing or we are searching for that particular satellite. So we know the code. But when this is important to remember this stuff here. When I get a few samples of the incoming signal, I don't know the delay. I don't know the difference. So they will not align. And so what I do, I keep sliding my local generated signal. I keep sliding it over the received samples until I get a match. If I get a peak, then this is first indicator. Oh, this satellite signal is present in the air, and the delay was the difference here where I get the match. So we go back here. In the first type, we generate the PRN code. We slide it over the incoming signal. But in this case, what we do, we also shift the carrier signal. This is our local generator or local oscillator. We generate the frequency using this small unit in my hardware. I get two streams of that. I don't want to complicate things, but we will see later why we need two streams of this. We get the in phase. This is the same phase, and we generate another stream of the same signal at the same frequency with initial guess, let's say, but at a 90 degrees phase shift with respect to this. We compare both streams with the incoming signal. So now we have to, we need to like focus on these two blocks now. We are generating a code and we are generating a carrier frequency, but these could be like totally off or far away from the incoming signal. So what we do, we search the whole space. We set a threshold. For example, for the Doppler, we say we will search from the GPS nominal frequency minus 10 kHz to we shift with 0.5 kilohertz every time, and we move until we get to the other end. That's plus 10 kilohertz. For the code, we generated a code first time with the zero shift. If we didn't get a match, we shift it by one chip to the right or one bit, and we multiply the signals again until we get a peak. So what's the problem with this? We will find if the signal is present, we will find it for sure. However, it is too slow. As you will see here, the combinations. If we go through this example here, this is the number of iterations or search processes we will do. So 41,943 iterations. If we go from the like low end to the high end of the search space, and it's 2D, so that's a lot of time. The other way to did you get this, or shall I repeat it, or we just go to the other types of acquisition algorithms?
I have a question here.
Yes.
We are using binary phase shift keying for modulation, right?
Yes.
So why do you need the in phase one? So binary phase shift keying only produces the a signaling quadrature phase.
Because you will see later when we track, this is just acquisition. We need to uh, like two streams. You need them for the tracking later. You will need two copies so that you see if you are getting high power. If you are not aligned in phase, you will get some of the signal power. If the signal is present, you will get some power of this quadrature thing. So you need to keep the maximum power in this in phase stream. How you measure that? You will see later there is something called discriminator. It tells you how much power you are getting at this and how much power is this. If the power is higher here, or for example 50%, then you need to shift this by a certain quantity or amount in phase so that you go to maximize power on I. I believe you will get it later, like in shortly in some of the coming slides.
Okay.
So now instead of doing this intensive search, there is another way of doing that. We can save some of the search steps or iterations. And this mode or technique, which is called parallel frequency space search signal acquisition algorithm. In this case, we search only the possibilities for the code phase. So how many possibilities? We have 1,024 operations. Or sorry, 23, because if we shift by 1,024, we will get back to the zero place, right? So this amount only. How we do that? We don't search in frequency now. We generate every time we generate the code replica. First time at zero offset or zero shift, then we shift it by 1 bit, then 2 bits, and every time we apply Fourier transformation. So if the satellite signal is present, what will be the output here? Because we are applying Fourier transformation, we will get the frequency here. We will get the frequency, initial estimate of the frequency at which the signal is arriving. So this helps us save lots of search space, but the complication here is the applying Fourier transformation, as you know. Uh, this could be measured in complexity as well. Someone might say, and we all know that we will apply fast Fourier transformation, right? But the complexity is still there. It's not only saving time. So with this, we search parallel frequency, means we search the code possibilities, but no search in the frequency space. In this mode, which is called parallel code phase search or search signal acquisition algorithm, it's too lengthy. So in this case, we search only for in the frequency bins. By the way, the steps in the bins we call in the frequency we call them bins, and in the code we call them chips, like bits or chips. So in this mode, as you see here, we generate the frequency in the numerically controlled oscillator here. We still need the I and Q. We hit the incoming signal with that. We apply Fourier transformation here, but we generate the this code once. We generate the code here, and we apply Fourier transformation. We take the complex conjugate out of that output. When every time we change the frequency here, we only shift the frequency or the phase of the signal, but we generate the code at once. When applying the inverse Fourier transformation here, it will give me the because this is in time, right? When we apply inverse Fourier transformation, it will give me an output in the time domain. That output here will be the shift in the code. Since I know the frequency I applied in the last search step, I'm looking for the delay on the code. So this will be the output of the inverse Fourier transformation here. So it is much faster, as you see, but again, applying Fourier transformation and the inverse Fourier transformation is a complicated or a complex process. So we have 3 modes or algorithms to apply signal acquisition, but all of them are intensive operations. So that's why we need signal tracking. Now think about, I mentioned this many times before, like even if we think about stationary receiver, my hidden parameters are changing, right? The rate of change, the range between the satellite and the receiver, and the rate of change of that. So we need to keep a track of those parameters. I cannot apply this acquisition step every time I get a set of samples from the received signal. I cannot do that. That's very intense and complex process. Avoiding that, we switch to signal tracking. we must track those changing parameters. So what's the purpose or the job of the tracking system or loop or block as you see here? It's to refine the initially estimated variables and to keep tracking them so that we could stay aligned with the incoming signal. Again, the acquisition provides rough estimates. The tracking on the other side refines those quantities and maintains them, which ensures we extract the right navigation information out of the receiver. If you look here, we have a tracking step, then we have code tracking running concurrently with the carrier tracking, but it's not completely independent, but they need to be treated differently. They are cooperating, they are exchanging information, as we will see the details later, but at the same time they have different characteristics for their tracking mechanisms. Once we refine those coarse measurements and we keep track of them, we can then extract the navigation message. So this is another view of one tracking loop. This applies to both code phase and carrier frequency tracking loops. They use similar mechanisms, but they have, for example, we will talk later, we'll show some examples of those discriminator function. You will see they need sometimes different discriminators. So the goal of the signal tracking is to keep the locally generated replica. We generate every time this is the loop, we estimate how much difference between the incoming and the local generated signal, and we keep adjusting ourselves. So we keep the locally generated replica aligned with the incoming signal in both in time and in frequency or in phase. This discriminator here measures how much the difference is. This for the code phase, it will tell me your signal is a bit advanced in time or delayed. In frequency, it will tell me like your estimated Doppler is higher than actual or the incoming or less than that. So I keep adjusting myself. Since those quantities could be temporarily affected by some other interfered signals, for example, and other stuff, we should keep them in that low frequency scale, so we avoid high frequency signals, which normally represents noise. So we apply low pass filter. Out of that we control or we adjust our numerically controlled oscillator. So my estimation this time should be better than last time, and we keep into the loop. We'll keep back and forth around more or less the estimated or the incoming signal. Sometimes we'll be a bit advanced, sometimes we'll be there will be fluctuation in the obtained results, but it should be around the signal of interest. Any question here? This is how we do the code tracking. Now, I want you to pay attention here. We mentioned that we need to keep aligned with the incoming signal. Now we are talking about time, the delay. But we cannot do that with one signal like replica. So in code tracking, we generate 3 replicas instead. We call the first one early, which is slightly ahead of the correct alignment. The second one, or the middle one, is the prompt, which should be perfectly or ideally aligned with the received signal. That's our goal, to keep one of them aligned with the incoming signal. This is, let's say, the bit of the incoming signal. and we generate 3 bits. Our goal is to keep this prompt aligned with that. The late one is slightly behind, as you see here. We generate those 3 replicas. Let's say now we know the frequency perfectly of the signal. So we generate 3 replicas at that exact frequency, but they will be delayed. We compare them versus the incoming signal every time. The receiver compares the like the correlation values. As you see here, the correlation, the maximum value is 1 and the minimum is 0, as we discussed earlier. This shouldn't like, doesn't have to be 1, but we normalize the values, right? So the maximum we get is 1. So the receiver compares the correlation values between early and late signals to maintain proper alignment. If they are like unbalanced, it may indicate sometimes error sources or for example, if we have a multipath in our signal, those in good estimation, those sides of the triangle should have like same slope. Of course, one minus 1 and the other one is 1, but they should be like this triangle shouldn't be squeezed like. But in many cases in real life, if you plot this correlation function, you will see that this is never true with real data. So this should be at 0.5 and this should be at 0.5. That's how we balance this. But in real life, you will see, for example, this is 0.6 and this is 0.4 and so they keep going up and down. There will be fluctuation. Now, this may also answer your earlier question, but this has to do with the code. Why do we need, if the input to my correlator is the late and early now to keep aligned, why do we need the prompt? We need the prompt to extract the information. If I am aligned with that, I can hit those 2 bits to get rid of them. I can how can I do that? Like this is how demodulation works. If those 2 bits are aligned, I can remove this extra bit from the code and I keep only the navigation message bit, which is the thing I'm looking for or interested in. This is how the code tracking loop. Remember, when we discussed this here, we were talking about general tracking loop for both. This is a general idea. Now, we mentioned that for a code tracking loop, we need 3 replicas of the signal delayed in time, but at the same frequency. You might be shocked when you see that for all these 3, for the prompt, early, the prompt, the late, we will generate 2 replicas, one in phase and the other one like in quadrature with the incoming signal. Because again, we need them for the carrier tracking, as we will see next. But here, by continuously measuring the misalignment between the received and locally generated signal, if the prompt, like we measure the output, we mentioned earlier this discriminator takes a combination. You will see there are many discriminators in literature, and you will see they are different using different inputs or different combinations. So using the input to this, for example, in our case, we are showing here dot product, and this is how this dot product discriminator works. This is the model for that. We calculate the output of that, and if the prompt signal is ahead, we shift it back. We shift the our estimation or locally generated back. If it's delayed or if it lags, we shift it forward. So this loop maintains synchronization as long as the receiver maintains lock to the satellite signal. What does that mean? If the signal is lost, for example, temporarily or briefly, the last estimated value can be reused. We know initial rough estimation, right? If we lose the signal for a very short period, we still can avoid the repeating the acquisition process. But if we lose this for too long, then the acquisition step, unfortunately, must be restarted. If you look at this here, our main focus, as you see, this is the biggest block here, right? We generate PRN code generator, assuming we have in-phase estimated signal and quadrature phase estimated signal. Where are these coming from? These, as you will see next, they are coming from our code tracking loops. So again, this works independently, but concurrently and cooperatively with the carrier tracking loops. We use here different stuff, but we use input signals coming from the carrier tracking loop. As well, we will see later for the carrier tracking loop, we also use output from this code tracking loop. Any question about this?
Just a question regards the previous slide, please, Doctor. Yeah, this one.
Yes.
And based on this also, we can estimate the time delay or?
Yes. So the goal here is to keep aligned with to keep this prompt replica aligned with the incoming signal. If we succeed in that the time, because we have a reference time here, right? The amount, this signal is shifted from the time we start with, from like zero shift. That's the delay. That's what we are looking for indeed. The purpose of the early and late is to keep this balanced correlator. And if we succeed in that, if we could do that correctly, then we measure how much this prompt signal is far from this like zero shift replica. And that's the delay. That's the target out, like, or the outcome of this this tracking loop. We are concerned here about we are interested in the delay on the signal. Does this answer your question or?
Yeah, thank you, Doctor.
On the other hand, like we here assume that we have a prompt replica, as you see here. This is coming, this is the output of this. Like we have the prompt here generated here, right? So we go back, we assume we have a prompt replica code signal. We use it for our as input. We multiply it by the incoming signal. This multiplication, you see it as a correlator or multiplication or whatever. Indeed, if you see the real like implementations, you will see that we remove this. We remove this stuff since we know it to a good like extent. So now we correlate this with the incoming signal. We use that for the two locally generated replicas of the signal at the same frequency. You see here, our last estimation provides us with a good estimation for the frequency. We create a cosine and sine versions of that signal. So this is the in phase associated with the cosine, and this is the quadrature. A few seconds, please. My screen is dim now. Yes, so this discriminator here, this may answer your question earlier. The output, the metric or the quantity we get out of this should tell us how much we are far from the actual incoming signal frequency and in what direction, if we are left or right to that, and the quantity. That's why we need two of these. This arctan will tell me, and with my, by the way, with my adjustment every time, I try to keep my in-phase signal aligned with so the total signal power or the measure part of the signal power should be in the I arm. And we should minimize the power on the quadrature so that the signal will be aligned. Why is that? Because this is associated with the cosine, right? And again, I am interested in the cosine term so I can remove it because it's a mathematical requirement here. When I get the cosine aligned with another cosine, the difference between the two angles is too small. The multiplication of the two will give me the cosine, the sum, and cosine the difference. So what I do with the cosine, the sum, can anyone answer here? If I have two terms now, one scaled by cosine the difference, and this difference is too small because my estimated frequency or phase is close to the incoming one. So that will be cosine of nearly zero. We consider that one. How can we exclude or we get rid of the other term which has the sum of the two angles? What should I do if I have a high frequency term within my incoming signal?
In filter?
Yes, that's why another reason here to apply a low pass filter, right? So
Yeah.
we apply low pass filter, it will allow the low frequency signal, which is almost DC. When I have cosine of nearly zero, that will be close to one. So what's left is the navigation message and the code bits. So the navigation message bit comes at a very low frequency, which is 50 hertz only, compared to this high frequency. This is in intermediate frequency, normally in tens of megahertz. By the way, we mentioned earlier, we down convert. We don't deal with the gigahertz frequencies here inside the circuitry. So we down converge to something, for example, in practical cases, it could be 38 megahertz, for example. With this cycle, those two blocks cooperate concurrently, so we keep track of both parameters of interest, the code phase, which eventually represents the delay on the signal, and the frequency, which represents the Doppler on the signal, so we can adjust ourselves in both search directions. Now, these are some examples. If you search literature, you will see many of them. And everyone if you plot the characteristics of the curve of this, you say sometimes you get, for example, discontinuity, right, or an infinity value. So, for example, within some range, that discriminator might work perfectly or even ideally, but in some circumstances, it can destroy the whole solution. That's why sometimes it's empirically you need to try the different discriminators. By the way, some of them work better for code phase, some work better for carrier phase, but some are also dedicated for frequency, as you see here. For example, for vector tracking, we may talk about it later a little bit, but for vector tracking, we are interested in the frequency, not the phase, the actual amount of the frequency. So, for example, in our lab, we implemented this before in our vector tracking software-defined receiver. So you need to get more familiar with those. You see this works good for code phase, but you see the square operations here. This might also take like extra time and memory, right, to compute all of these terms for the square root. So you need to judge yourself and search for the best discriminator function that fits your needs or your application. This is, by the way, this is well known, and this is called early power minus late power. It's normalized as you see here, but this is the early power, the sum of the power on or the samples on the prompt sorry, on the in phase plus the samples on the quadrature squared, you will get the power, early power, and this is minus the late power. We need to keep those, as we mentioned earlier, balanced. For today's lecture, all of this stuff I mentioned earlier, you don't need it for the course, by the way. And to be honest, you don't need even to go through them. But sometimes we expect some of you might later work on this deep level of measurement inside the GPS receiver. So this is a good conclusion indeed, collected through years, and indeed, like you might find them useful as a source for your implementation. So you will find more information here about this is the basic tracking loop. The problem was, like, this looks like a control problem, right? So you have the low pass filter and what we call this, what's the numerically control oscillator? From here, what's this function? Anyone can guess or knows what's this? In Laplace transformation domain, what's 1 over S?
Integration.
Yes, exactly. This is integrator, right? So this is how the problem is depicted. We have a low pass filter, we have integrator here, and our goal is we have the correlator here. Every time we want to minimize this error, we want to minimize the difference between the incoming signal Y of S and the signal I generate, either in time or in frequency. So if you take what's this, by the way? What's the Y hat over Y here? What does this mean? What term is this?
Output over input, or
Yes, but what we call this normally?
Transfer function.
It is transfer function, but like to get more like this is how we control our gain, right? So the gain term is hidden here. These are that, like, some people thought about this and they wanted to uh, formalize this, so we get into the, instead of traditional tracking loops, we get it into like adaptive gain problem. So they derived it, they started with this. Yes, this is the transfer function, and they did some work on that, some substitutions. They reordered the terms and they got inverse Laplace transformation. So what does this remind you of now when you look at this?
Kalman filter, or
Yes, exactly. Yes. So that's why they switch from that traditional, the thing you need to think about here to resolve this is to, like, think about a variable gain filter. So this fits perfectly with Kalman filter implementation, by the way. By the way, you will see, I tried that one day, but I gave up because of some other, like maybe I didn't have enough time. But you will see some people apply Kalman filter smoother, let's call it smoother in this case, for every channel inside the GPS receiver. You track those variables for every channel. By the way, for the tracking loops here, it's something complicated inside the receiver. For each satellite signal, you need to dedicate one channel. And if you look into hardware implementations in the past, every receiver had 12 channels. Why is that? Because normally we would have, let's say, maximum of 10 satellites available, right? But can anyone guess why do we need, for example, up to 12 or even 14? Why do we need to in hardware? Because that costs money and that adds complexity, right? So why shouldn't we just have, for example, 8 or 9 channels? Normally or typically, we had 12 channels. Now I'm talking about GPS receiver only now with the multi-constellation case, you should have more channels dedicated for each. But that traditionally was because in many cases, especially in downtown environments or like in urban circumstances, will also have a reflected signal that we don't always kill that multipath signal. Sometimes that could be constructive multipath. That means we may get we dedicate two channels to the same satellite signal, and then we judge, we combine them, or we get the better one, or we can, yes, judge, oh, this is the actual and that's the delayed. So in some cases we need to track multiple replicas of the same satellite signal. So again, now you can apply, but you know that there will be some complexity here when you apply CAML filter for each unique channel individually. This brings us to the vector tracking architecture. How are we doing with time? We don't have so much left, so can we just continue today?
Yeah.
Yeah.
All right. So traditionally, we track every, we dedicate one channel to track the code phase and the frequency over or out of each satellite signal. In that case, we'll have N of channels, right? We merge them only at the navigation processor. We merge the pseudo ranges and pseudo range rates, even in tightly coupled fashion. We calculate the navigation at this here independently after we get the output of each channel. So if there is no enough power on one channel, that channel will fail. If we don't assist that channel, let's say the signal power here was a bit little, like less than the, if we set a threshold, for example, for tracking, if we decide if the power is below this threshold, oh, we cannot, we assume that channel is useless, and we cannot improve that quality of the signal due to some circumstances or error sources. So in this circumstance, in the traditional scalar tracking architecture, we can easily lose the lock to the satellite signal. And what happens if we lose lock? When we need to repeat that acquisition, especially if we lose that signal for a long time. So here, the number of inputs depends on the number of the channels, right? If we have n inputs here, the number of unknowns is equal to that. Let's talk about, by the way, for the code tracking loop, they call them delay locked loop. For the phase, they call them phase locked loop. Regardless the names now, how many channels we have? We have one channel here with two unknowns, right? Let's omit the phase now. We talk about the delays. We have n tracking loops tracking the delays on each channel. The output of that will be the same number of pseudo ranges. So the number of inputs will be equal to the number of unknowns. In the vector tracking, however, there will be some cooperation. Like you see, we shifted this block a bit earlier. What does this mean? We still compute the navigation solution at this block here. However, we merge somehow the tracking and the navigation in one Kalman filter. This is centralized structure. How we do that? Every time we estimate the locally, every time we estimate our position, we tell those channels if one of them is, for example, faulty or something like that. If this channel only is away from the best estimation for either the delay or the frequency, we can assist it. We can assist. We don't let this channel fails unless if it's severely away. If it needs only a little push or adjustment, we can tell this to adjust itself so we can keep it in the loop and we get better estimation. Why is that? Because in this case, we always, our unknowns, as you will see here, we always have the position and the clock bias unknowns for the position and for unknowns on the velocity side. If we talk only about the position, we most of the time number of inputs here, number of channels will be higher than number of unknowns. We call this case the overdetermined system. So the quality of estimation, the position and clock bias out of these channels combined will be better than the traditional case. Moreover, we can assist the channels. We give them feedback. Can anyone here relate, like how can we assist this channel using the information we obtain from this filter here, from the position and velocity? Can anyone guess how can we use this feedback or information from the navigation filter to assist these channels?
Maybe if we know the velocity of the satellite, we can.
We know the position and the velocity of satellite. Yes, we are assuming we know them, but in the tracking the signal while traveling, while propagating, it had some errors. For example, multipath, or we still know the satellite position and velocity accurately, but the problem is here inside the tracking loop. That triangle, if you remember, that triangle was not balanced. It was shifted or squeezed a little bit. How can I use this position and velocity information to fix the issue with individual channel? Because we mentioned earlier, the position calculations are based on the pseudo ranges, right? And the pseudo range estimation is based on the delay. After I get my position calculated, for example, out of 9 satellites, I can tell this tracking channel my estimation of the range is this much, so I can tell them to derive the delay, the actual delay or the estimated delay, when I have information exchange between the other channels. Now I have 9 channels cooperating to provide pseudo ranges and then velocity from this position. For example, I calculate the pseudo ranges and I tell each channel the range you should see is this much. With that, it can fix the tracking loop. It can fix the code delay, and this is like this is not only like a theoretical concept. We have even in our lab. I have implemented this in my PhD thesis, and we got great results. One thing here, those traditional will be in some cases more stable. If you have a failure channel, it will not affect the others, right? But here, sometimes like a malfunctioning channel, if you don't detect that, it might lead the whole solution to drift. Moreover, the complexity here of the vector tracking, you need to merge both the tracking stage and the navigation stage in one filter. That's not an easy task. If you work on this, you will see one day it is not an easy task to derive the feedback. The most complicated thing here is to what quantities you should feed, because those terms will be very critical if they have some errors inherited from your calculations. So this will be sometimes sensitive. By the way, for another reason, vector tracking based receivers are called sensitive receivers. They, for other reason, but just by coincidence, I use the term sensitive here. So this implementation could be fragile sometimes. If you feed the wrong information, you may destroy the whole tracking loops at once. So I left some extra information here. I made up those slides by myself. There is a big effort here. You may appreciate one day if you worked on this. You will see how we, for example, how we connect the code phase to the delay. You will see the error term in there. You see how we could, here's the error term, how we connect the code phase error. This is the code phase. That means the delay. When you want to estimate the delay, you need two quantities, right? Your actual minus the estimated. How is that connected to the pseudo range? This applies to the frequency if you have a frequency discriminator, and for the carrier phase. You will see here also how is this connected to the position I mentioned earlier, because if we subtract the position from the like the actual and the estimated, that's indeed the error in the code itself, right? So that's directly from the, instead of the range, that's the error in the position could reflect into the delay. That's how we implement those vector tracking loops. Same thing, the velocity reflects on the frequency, the velocity of the receiver, the actual minus the estimated, reflects on the frequency of the receiver. And this is just the another notation of the line of sight. If you wanted to implement that one day, you can find the transition matrix and the measurement matrix and how they are connected again with the error terms and all the details. If you are using, for example, integration with RIS or other INS models, you can like go up to the ultra tightly implementation. So any questions about this stuff?
Can you please share these slides with us, because I don't think they are included in the.
It is it has been uploaded as of last night, I believe. Just send me a reminder if you don't see them.
Okay, thank you.
And feel free, guys, all of you. There is more stuff, but we just want to keep it like you have lots of work on your projects, but there is we have lots of other presentations for our implementations for any sessions, like any sensor you are expected to work on in the lab. So we can help you with some stuff even after you finish your course.
Thank you.
How are you doing with project 2, by the way?
So this is Nick. I'm not doing so well with it. My receiver is basically bouncing around the world and is showing a speed that's not consistent with a car. I have been talking to Joseph about it. At first, he had the same issue, but I think he got it fixed. Over.
Yeah, did you fix for the satellite clock that's given in the data set? When you see this bouncy effect, normally it is because you missed to correct for the satellite clock. There is a term in the data set, Joseph, is it called DT, I believe? So at
Yeah,
every
it's the DT.
yes, at every epoch, you need to correct the measured range for the satellite clock before you use it in the least squares algorithm. Please try that, and always, like, even if the results are meaningless, just please share with me a plot. I might save you lots of time if sometimes I can capture the mistake without looking into your code. So just me any preliminary results, and if you fix the satellite clock and the issue is still there, just share me with whatever you see in the in position, and if you are doing velocity calculations, we might catch it because I have seen lots of issues in this regard before.
Sounds good. Thank you. I will try to tackle that, and if I don't have an issue, if still have issues, I will contact you by tomorrow.
No worries. I believe so the classes has ended. I believe Dr. Abdul Majid is not teaching as well next week, but I wish you good luck with the course and your programs, and feel free to. I don't feel like just please share with me your findings and if you needed any help at any time.
Doctor, I have a few questions if you don't mind. Just I think it'd probably be helpful for everybody on the project
worries.
too.
Do you
For
have
the calc
do you have the ability to share if you wish to share the data set or something, or just go ahead now?
I could share my screen. Um, yeah, I'm having issues with. You see my screen up?
Yes, we do.
Let's see. So yeah, the thing that you were talking about with Nick, I think DT was right here, yeah. But my question is for the R matrix.
No, can you click on that? This is
Yeah.
the for each satellite you will see. So that's one by. Oh yes, inside that that's a cell.
Yeah. So there were 6 satellites, so there's going to be 6 DTs
Mhm.
in that APOC. For calculating R with the Kalman filter, I don't see in the data set anything related to the Doppler standard deviation. I only see um, the um, the range. So at least in your example, you
We get
calculated R.
we get that from the position, right? Not the velocity. So we use the same to feed Kalman filter standard deviations of the positions. That's the standard deviation of latitude, longitude, and altitude. You will see them somewhere. Again, empirically, you will find they are sometimes when you tune your filter on your on empirically, you may need to scale this with meaningless quantities until your filter is converged. Like, did you start now? Where is your R matrix?
R matrix is let's see. Here. So yeah, for the standard deviation for the range, it's here, but then I don't see anything related to the Doppler, so I just put ones because
Oh no
in your
no
example
there
you
is
mentioned it.
something. Yeah. Sorry, I thought I was thinking loosely coupled. So you are working on the Kalman filter for GPS only case. Yeah, there should be. Sorry, I know. I remember one postdoc in the lab one day. He said you need to spend 90% of your time and efforts on the data set to get a working
Yeah.
data set, and 10% is for the coding. So I understand. I saw uh, something like if you go back to the data set to their workspace, you should see it maybe inside another. There should be standard deviation for Doppler measurements. Did anyone get to this stage, guys? Can you go into this Doppler L1? That's only the measurement itself, right?
Yeah. Like I looked through everyone and I couldn't find anything related to it, but I may be wrong, but I didn't see anything.
Eric here. I couldn't find anything related to it either. I just calculated my own standard deviations for Doppler.
Okay, that's another idea. He did like he got the this term calculated out of this data, but I will double check and let you know if you are totally missing that, or we can like start with a seed on our own. But I thought it is like even for this GPS only data, there are multiple files, right? One is called Novatel, blah blah, and sorry, I haven't seen this for a good while, but I will search it. And if I didn't get back to you within 24 hours, please just send me a reminder. We
Okay.
should find it somewhere. Now go
And
back to there is another issue. It's a coding issue. Sometimes in MATLAB space, when you have number of satellites changing, like you have, for example, 7 or 9 pseudo ranges, and in the next epoch you have only 8. and the order would change. So what I do, I delete every time I delete the last measurement after you finish using it. It's a good
Yeah,
practice to, yes, yeah, that's a good idea. Yes. Sometimes you get something wrong because you didn't clear your space before the next epoch.
and sorry, another question. In the calculation of the F matrix, you have delta T, like large capital T. Is that just 1 second?
Yeah, that's 1 second, given the fact the measurements are arriving at 1 second here, but we normally scale it with the, yes, the sampling frequency.
Okay.
All of these are given at, for the GPS are given at 1 second. Yes, you are right. And by the way, don't forget when you do the integration, that's a very good question. Now, the uncertainty of the process, like the process covariance or noise, the Q matrix should be scaled by delta T, because your uncertainty after, let's say, 1 complete second is not the same as one after like 1 millisecond, right? You
Yeah.
are more certain when the your estimation is calculated after 1 millisecond, you are more certain about the state. So we always scale Q by delta T. In this implementation, it's just simply 1, but it's good practice to have it like initialize it in the beginning. You scale that by delta T, and then you look what delta T, actual delta T is.
Okay. And sorry, one more question, if you have time. In the row C1 standard deviation, so the pseudo range standard deviation, is that given in radians or is it in meters?
No, because it's the range is measured in meters, so this quantity should be in meters. No radians here. The radians only applies to position, geodetic position, lat and long, or the attitude information.
Okay.
By the way, if you have time, there is something published by NASA about the standard deviation of ranges and pseudo ranges and every this stuff. There is a good technical report. I have it somewhere here. If you need it, I can search for it. And you will see again the first question I was asked in my PhD defense by Dr. Georgia in I believe geophysics department at Queens. The first question she asked me, she said, "How did you where did you find the pseudo ranges like standard deviations?" So I told her I got them from this like NASA's report, but I tuned them like they were dramatically off. So she says, "You are honest then." She says, "If you say I use those, you will be lying." So she has the same experience. No single person used those exact amounts. We need to scale them. So those numbers are reported by NASA, by the way, long time ago. But you need to add a scale factor to this R matrix every time until you get your filter converged to a good solution.
Okay.
And again, please always send me. I can sometimes tell you the cause of the drift or the of your Carmel filter solution. Again, we mentioned this earlier. It will not give you maybe a better solution over least squares in terms of RMS, but that solution will be smoother. It will be like a soft curve, not spiky like the least squares. It will be up and down around but the Carmel filter solution, in the worst case, it will work as what we call it, a smoother like. The solution will be much smoother. And again, we mentioned earlier, this helps, for example, for vector tracking, you need Carmel filter. I did both, for example, I implemented both, but when you use Carmel filter, it helps you to raise the signal 2 dBs over when you use the least squares. 2 dBs is a very good number, right? If your signal you are like tracking a weak signal, when you use Carmel filter, you could raise the power on that channel for about 2 dBs. So because the solution is smooth and stable, not going up and down. but it will not give you like a magical solution over least squares.
I have a final question. In the project 2 document, it says code should be emailed along with the report. Is that still true?
I'm not sure. Maybe Dr. Nordin inserted that like I didn't check. You know, there are multiple projects I work on, but if that statement is there, then
Okay.
it applies.
Well, this is Nick again. The last project, Dr. Nurdin was very adamant that we did not put the code in the report. Over.
All right, you then better like reach out to him. He says you don't share your code, right?
That was what he said for the first report. Over.
Yeah, then if you wish to show something like new, you could just add a flow chart or pseudocode if you wish. Then if he doesn't want you to show your code. Any other questions?
Yeah, I have a question.
Yes, yet.
I sent you an email asking if there's any recording for lecture 3 from any previous years, if because our lecture wasn't recorded.
Yeah, because your email was directed to Dr. Majd, right? I was copied, so that's why I didn't respond. So I can later reply to that.
Okay, thank you.
No worries. There is a version, but you know there will be overlapping or sometimes because we not every time we talk the same. So but you will see everything covered in the other videos, older videos. But maybe sometimes you miss part of this lecture. You will find it in another video. But I will search for whatever you are looking for and reply to you then.
Okay, thank you so much.
No worries. Okay, guys, it was a pleasure working with you, and let's keep in touch then.
Thank you, Doctor.
Thank you.
Thank you.
Thank you. Have a good day.
Bye for now.
Thank you.